example here for isolated binary evolution, we kind of have two different paths towards a binary black hole merger. And in both of these paths, before you form a black hole, before an instability kicks in your star, you lose the hydrogen envelope. For example, above here, you have first a phase of Roche lobe overflow, and then the stripped star here in pink will form your black hole without having a hydrogen envelope. And then you go through common envelope, and again, you lose the hydrogen envelope of the common envelope and you form a black hole. So this is one motivation to not care about the hydrogen envelope. Or in the chemically homogeneous evolution scenario, where you have a very tight binary, where the two stars are steered by rotation and fully mixed, you never really develop a core envelope structure and the whole star becomes a helium core. So this is the motivation why I will not deal for most of the results that I'm going to show you here with the hydrogen envelope of these stars. Although I'll come back to it. Yes?
May I ask?
Of course.
So if you do not have this hydrogen envelope, what do you have for the common envelope? Is it helium expanding, or you just remove it but then assume it's there?
No. So in the models I'm going to present to you now, we don't do full simulations of this entire process. We just simulate the physics of the explosions, and then we assume that the physics would not be very different if you started the simulation at these points. But really simulating the whole thing, including pulsational instability, is way beyond the current capabilities.
Okay, great, thanks.
Okay, so we need a big core and a helium core. And why does it need to be very big? That's because we want the star to be radiation pressure dominated, which means the star is held up against its gravity by the pressure of photons. And if you have a core that's after wind mass loss, but before the pulsations, is about 30 solar masses, that guarantees that you're gonna enter the instability region. And the instability per se is not a new idea. As you can see from this very long list of references, the original idea is from the 60s. However, there's been a lot of work recently because of the detection of binary black holes. And I also want to give credits to Stan Woosley, who was the first one to really be able to compute through this entire process with his code. And the idea is that if you have these conditions and you let the star evolve, it will lead to an explosion. And this explosion are the theoretically best understood stellar explosions of massive stars. So let me finally walk you through what is precisely this instability. We start with a helium core that is burning in its center. It produces a carbon-oxygen core, and before it runs out of fuel, a layer of the star of the carbon-oxygen core can become unstable. This is because we start having photon-photon interaction that produce an electron-positron pair. This removes some photons, so effectively it softens the equation of state, because the equation of state was dominated by the radiation pressure. If you soften the equation of state, the star is going to collapse a little bit, which is going to increase the temperature and increase the rates of the pair production. So we have a runaway collapse of the star with a core that is still carbon-oxygen. So it's still rich in nuclear fuel. And as the collapse keeps on going and the temperature increases, at some point, you trigger a thermonuclear explosion, typically of oxygen or of heavier fuels. And this thermonuclear explosion can have three different outcomes. The first one that was already realized in the late 60s is the so-called pair instability supernova. In these cases, the thermonuclear explosion here releases more energy than the entire binding energy of the star. And so all the gas flies away and you form no remnant. already in the 60s, they were not able to run the simulations, but they realized that if you lower the mass of your star a bit, then this explosion is going to be less energetic. So what's going to happen is that the explosion is going to puff up your core, expand it and cool it adiabatically. So this will shut down this burning. But as the core expands, it will trigger a shock wave in the outer layers that can eject some layers of mass. And that is called a pulsational pair instability, because your star does a pulse, ejects some mass, but then it relaxes. As it relaxes, it cools, emitting neutrinos, losing entropy. And then the star can hit the instability again and loop through this circle a few more times. And each time you lose mass, you have a pulse. And at some point, the consumption of the nuclear fuel, the ejection of mass, and the loss of entropy every time you relax will stabilize the core and get it out of this instability region. And once the core is stabilized, it finishes its evolution normally, burning stably whatever is left to burn. And in the end, these stars will most likely form black holes, maybe with, maybe without a final explosion. The third possible outcome is instead for stars that are even more massive, assuming that they exist. And in that case, the evolution proceeds exactly the same at the beginning, but this thermonuclear burning happens at such low densities that every new nucleus that is formed in the explosion is immediately photodisintegrated. And so basically all the nuclear energy available is used to pack and unpack nuclei together. None of this energy becomes kinetic energy of the gas, and in the end, you still form a black hole. And so this cartoon tour of pair instability evolution should also suggest to you why we expect a gap in the black hole mass distribution. Because at the low mass end, we have black holes whose mass is determined by how much mass they have lost in this process. Then we have the pair instability supernova regime, where you form no black hole. And if stars sufficiently massive exist, you will form black holes again. So let's have a look at the predicted pair instability gap.
Matthew, before you proceed, yes. Could I ask a question?
Yes, of course.
Why do you need the star to be in the carbon-oxygen burning phase to get the pair production? Is that because of the density or the temperature?
Yes,
can't you do
correct.
that in helium burning?
So in principle, the pair instability doesn't care about the composition. But to get to the pair instability, you have to be hotter than 10 to the 8.5, 10 to the 9 Kelvin, and lower density than about 10 to the 4. And so those conditions are reached in the cores of stars only after helium core burning. So it's not a chemical requirement, it's just the thermodynamic condition that give the runaway pair production or happen at conditions that are beyond helium core burning.
Okay, thank you.
Sure. Okay, so this plot here is showing you the pair instability black hole mass gap as predicted from naked helium star models. The gap is between 45 and say 120, 130 solar masses. And here you're seeing on the x-axis in the bottom, the initial helium core mass of my models, which decreases because of wind mass loss and then possibly because of these pulsations. And on the top axis, you're seeing the carbon-oxygen core mass, which is a more robust metric because it's less sensitive to the wind mass loss. And so here you see that at the low end in blue, you see stars that are too low mass to go through the pulsations. And these produce a one-to-one relationship between the black hole mass and the final core mass, basically. Here we assume that the whole helium core will collapse into the black hole. In green, instead, you have stars that hit the pair instability, and as you grow in mass, this pulsational pair instability remove more and more mass, causing a turnover here in the mass function. And so how much mass is lost in these pulses sets the the maximum mass below the gap, which is at about 45 solar masses. Then for carbon oxygen core masses above 55 solar masses or so, you hit the pair instability where you have no black holes. And for carbon oxygen cores above 120 or so, you find black holes again. And I want to emphasize that this result is one of the most robust predictions that one can make in the evolution of massive, very massive stars. And most of the papers in the literature have a quite good agreements with each other. The main uncertainty, again, is the fate of the envelope for models in this range, models that don't pulsate if they have a thick hydrogen envelope. And if the envelope can fall into the black hole, then these could make more massive black holes, maybe. And I'll get back to this issue. But the physics of the instability per se and how it works in helium cores, at least 3 different groups that can run this simulation kind of agree on the numbers. Just to showcase the robustness of these results, this plot shows a zoom in on the bottom left corner of the previous plot. So we're showing again the black hole mass as a function of the carbon oxygen core mass. And now each color here corresponds to stellar models computed at different metallicities. So you can think of these as stars in different galaxies throughout the universe history. And as you can see, the range in metallicity goes over about 2.5 orders of magnitude. And over such a wide range of metallicities, the maximum black hole mass below the gap is varying by about only 7%. And so this is interesting because it means it might be possible to standardize the maximum black hole mass below the gap and use it as a standard siren, like we use standard candles for the supernova 1As and do cosmology with these. This, of course, requires that the pair instability gap that is predicted doesn't get too polluted. There is, however, one physics ingredient that really matters for these simulations, but hopefully is something that is constant throughout the evolution of the universe. And what matters is the rate of this particular reaction rate, carbon-12 plus an alpha particle that goes in oxygen-16 and a photon. And this reaction rate is important because it governs the end of helium core burning. Once the triple alpha has produced a little bit of carbon, then you can do carbon plus alpha to finish off the alpha particles that you have. And so the rate of this reaction determines the carbon to oxygen ratio in your core. The more carbon you have, the thicker carbon shell burning can develop. And if you have a very big carbon shell burning, it can stabilize your core, making the core smaller effectively. And so here, again, the y-axis is the black hole masses, and the x-axis now is the rate of this reaction. If you decrease the rate, you're left with more carbon, the core is stabilized, and the gap is moved upward. You need to be more massive to hit the instability. Instead, if you increase the rate on the right of these plots, well, at some point you run out of carbon and there is no carbon anymore. And then the gap is not that sensitive to this parameter anymore. But interestingly, the width of the gap is fairly robust. Both edges move in the same way. And there is a range between 100 and 130 solar masses that cannot really be reached playing only with this reaction rate. So this is interesting because, again, if you're able to detect where the edge of the gap is, we might be able to use gravitational wave detections of black holes far away in the universe to constrain nuclear physics. And again, the condition here is that we need to be able to find this gap in the data. And I want to go back to this plot where there is this feature. So I would argue that this feature is the most robust evidence for this process happening in nature to date. Why do you expect a feature? Well, because you can make black holes slightly less massive than the maximum, both from low mass black holes, low mass progenitors that don't lose much mass in the pulsations, or very massive progenitors that lose a lot of mass in the pulsations. And the fact that there is a feature between 30 and 60 solar masses and a pileup of black holes there is really suggestive that this process is acting in nature. And of course, here I'm showing you just one fit to the LIGO data. Oh, sorry. Every model that allows for features will prefer features between 30 and 60 solar masses. And of course, this is the most, I would argue it's the most robust evidence for pulsational instability in nature, but it's not the only one. We also have...
Can I make a comment?
Sure. Yes.
I'm very impressed that we're seeing this peak in a log plot. I mean, it's a massive peak. It's not a factor of 2 or 3, it's an order of magnitude.
Yes. There is, so in this plot, this should be corrected, but LIGO is also particularly good at catching more massive black holes. So I believe in these plots, this is bias corrected, so that shouldn't matter, but that could be one of the reasons. And also more massive black holes will have shorter delay times just because they emit more gravitational waves. So there are a few selection effects that might help. And I wouldn't trust this is still based only on like 50 black holes. So this is, it's still tentative. The shape of this peak is going to change with more and more detections. But yeah, it's huge. I see there is another hand.
Yeah, just a question regarding this figure. Why is it that you consider only the primary or the more massive of the binary and not both of them?
Oh, so this is a choice that LIGO has made in presenting their result, a choice that personally I would have preferred if they gave us the chirp mass, because we can make chirp mass from theory, and the chirp mass is a direct detectable, a direct observable of gravitational waves, but LIGO has chosen to present the results in M1. But in principle, in like when we do population synthesis of this process, both stars could pulsate. And then if the second one pulsates and loses more mass, it will be the second black hole. But these, I mean, in my simulations, I'm simulating only single stars for the moment. So this is a choice that LIGO made in presenting their results.
I see, thank you.
Sure. Okay, if there are no more questions, yeah, I wanted to spend a few words on the other evidence that don't come from gravitational waves. And the point is there are direct detections of astrophysical transients that have been interpreted as pulsational perinstability supernovae. IPTF 14HLS is one famous recent example. The problem is that all of these detections are controversial. And the reason is people like me that do models predict a wide range of predictions for these transients. And these ranges of predictions are overlapping with the predictions of different transients, different scenarios for, I don't know, superluminous supernovae, magnetar-powered explosions, etc. And so it's difficult to have uncontroversial determination. Just to give you a flavor for the range of predictions and the trends that we get out of our models, I want to show you a few features. And in particular, the first one is the timing of the pulses. So here, this plot is showing you the delay time between the pulses and the final core collapse as a function of the carbon-oxygen core mass. And as you can see, there is a huge range from like hours to 10 to the 4 years. But importantly, I think, this range is not randomly populated. There is a trend. The first pulse will have a longer delay, of course, than the second and the third. But the more massive the core pulsating is, the longer the delay will be. And in the most extreme cases, these pulses drive the star so far out of thermal equilibrium that they cannot cool through neutrinos anymore. They have to cool through photons, and then to relax back to their equilibrium configuration and do a second and third pulse, it takes an entire Kelvin-Helmholtz timescale, which for a star with a core of 54 solar masses, carbon-oxygen core 54 solar masses, is about 10 to the 4 years. So there is a wide range, and there are many other phenomena that could produce transients on very short time scales or very long time scales. But also, interestingly, lots and lots of pulses should happen in a time scale of months before the final core collapse. And this is a very interesting range because we can actually see these in human lifetimes, so repeating supernovae, and we can probe these late mass ejections through, for example, intra-night flash spectroscopy. When you catch a supernova as it's rising, take lots of spectra, you can see the light going through the circumstellar material created by these pulses. The second thing that, oh, yes?
So just a quick question, since you have this plot here right now.
Yeah.
So for, say, about 100 years, you would have 45-ish
Yes.
solar masses, which probably comes from a star which is on the 80 to 100 mass range, which I believe is more or less the range where the primary in Eta Carinae is. I know that's a binary and there's other period stuff going on there, but could it be something like this?
So this has been, that's a very interesting question. And Stan Woosley has spent a lot of work trying to explain Eta Carinae as a pulsational pair instability. My personal take is probably not. My argument is that Eta Carinae is in our galaxy, and so its metallicity is quite high. Remember that this is the core, the carbon-oxygen core mass at the carbon-oxygen core mass is not so sensitive to the metallicity, but probably Eta Carinae has not yet developed a very a carbon-oxygen core mass this big. And by the time it will be helium core burning, it will have lost enough mass through winds that this core will not be this big. But I actually will mention Eta Carinae later. I think the best model for Eta Carinae that explains the morphology of the homunculus nebula as well and the skirts is a merger between two stars. So it used to be a triple. The two stars merged to form what is now Eta Car, and there is still the third companion that is now just the second companion.
Okay, thanks.
This is just my take on it. Stan Woosley might disagree with me, and he has done a lot of work on it.
Right, thanks.
Okay, so I also want to show you how much mass is removed, which in a sense, I already gave you the total or a flavor for a total by showing you the black hole masses, but it's also interesting to see how it is broken down between individual pulses, because these will shape the circumstellar material around these stars and determine whether we can see them or how transients from them will look like. And so again, here I have the mass lost per pulse as a function of the carbon-oxygen core mass. And again, there is a huge range from tiny mass loss of 10 to the minus 3 solar masses, which is definitely not relevant for gravitational waves because the error bars are way bigger, all the way to several tens of solar masses. And remember, here I only simulated the helium cores. So we did some tests with full stars, and we know that at the first pulse, if the star pulsate, the entire hydrogen envelope goes away. So to the blue points, if there is a pulse, you should add the entire mass of the hydrogen envelope that you have, which will be metallicity dependent. And as you can see, again, there is a trend. More massive models have bigger explosions that can remove more mass, and they end up forming lower mass black holes. And from the point of view of gravitational waves, the mass loss really becomes significant only above 40, 45 solar masses of the helium core. not because lower mass models don't pulsate, just their pulses are too weak to remove a significant amount of mass. And last but not least, just to give you an idea of what the circumstellar material around these stars might look like, I want to look at the ejecta velocity. And of course, here I have, in principle, a whole structure of the ejecta velocity. Each layer ejected can be ejected with some substructure. And like to study the propagation and the acceleration or deceleration of this ejected layer, radiative transfer would be important, which is not included in MESA. So here I'm just going to show you the velocity of the center of mass of an ejected layer. And here on you see these on the y-axis again as a function of the carbon-oxygen core mass. And as you can see, the ballpark velocity is in the thousands of kilometers per second, which maybe is not surprising because that's the ballpark of the escape velocity from a helium core. You can also see some trends that the second and third pulse might be slower than the first one, especially for these most massive models. And these indicate that the core has relaxed more than the surface after the first pulse. And so it was able to do a second pulse while the surface was still contracting. So at the second and third pulse, the radius of the star, the starting radius of the star was bigger and the escape velocity a bit lower. But what is also interesting is that this velocity range is precisely the width of narrow helium emission lines in supernova 1b ends. So supernova that show no hydrogen and show emission lines of helium. And I'm not saying that all supernova 1b ends are pulsational per instability supernovae. That would be crazy just based on an IMF weighting of stellar populations. But we know that supernova 1b ends are most likely a mixed bag. And it could be that some of these supernovae are actually pulsational per instability supernovae that we have already detected, but not interpreted in the right way. So, okay, if there are no questions at this point, I would like to move on to talking about the tail of the black hole distributions from LIGO and how can we make these forbidden black holes in the gap.
Quick question. So you have 10 to the 4 kilometers per second for the first pulse, then like 100 kilometers. These losses in them, are they similar or?
Sorry, you broke down a little bit and I missed the critical part of the question.
Sure. I'm asking, so you have the velocities, but are the masses in the second and third pulse equivalent to the first pulse?
The mass of I don't know by heart, but that will be on the previous plot. So for example, for the most massive one, the second pulse removes much less mass. And this is also something I can explain the physics of. That's because at the first pulse, you've burned oxygen. At the second pulse, you're burning products of oxygen burning, which typically means silicon. And the energy release per nucleon of silicon burning is much lower.
Okay. All right, thanks.
And as you can see, there is also some noise here because these are very difficult models to run just from a numerical perspective. And so I don't think this is necessarily the final answer, but the trend makes sense from a physical perspective.
All right.
Okay, so sorry, where were we here? So yeah, going back to this plot again, well, there is this huge feature, but then there is also this problematic tail that extends solidly inside the predicted per instability mass gap. And again, these are rare objects. So far, about 3% of the inferred existing population after correcting for the LIGO biases, but still, these exist apparently. And so how do we form them? Since this is a very recent discovery, of course, there's been lots and lots of ideas proposed around on how to make these forbidden, in quotes, black holes. And although I made these slides quite recently, I'm sure it's already outdated. But just to give you an overview, I would like to divide these ideas on how to form these black holes into two categories. Things that you can do to the star to avoid the pair instability, or things that you can do to the black hole after it is formed to grow its mass and put it in the pair instability gap. And in the first category, the first thing that you can do is mess with the physics of the star. I briefly mentioned that the C12 alpha gamma reaction rate has an impact on the black hole masses. Maybe if we decrease it enough, we can form black holes all the way to the masses that have been detected. However, I would personally argue that this is not a very good solution, because if you change by 2.5 sigma that nuclear reaction rate, you're likely to break other observational constraints like composition of carbon-oxygen white dwarfs, lifetime of helium burning, core helium burning stars, and probably you would also shift this peak towards higher masses. The other thing that has been proposed is to add physics to your stars. In particular, include physics beyond the standard model, and that effectively these models, what they're doing is they are allowing a new channel of cooling for the star, not only photons and neutrinos, but also some other new particle. And this makes the density of the star higher at any given temperature. And so at higher densities, the gas pressure is more important than the radiation pressure, and the instability can be avoided. But this again requires going beyond the standard model. And since there are other explanations, I would argue that this is not a satisfactory solution. Another thing that one can do is, instead of playing with the input physics, playing with the stellar physics. And so one scenario that has been proposed, and that I will focus most of the rest of my time on, is the stellar merger scenario. But another, and I will describe it in more detail in a second. Another possibility is make the cores of stars very small. If the helium core mass doesn't grow above 30 solar masses, then you don't hit the pair instability. But these also would break other observables in the universe, like the overshooting estimates based on the width of the main sequence for massive clusters in the local universe. If you instead want to act on the black holes after they have formed, well, you can try to accrete mass on these black holes, whether they're from stars or primordial. And one thing that I've worked on together with Salma's group is trying to have the black holes accrete from a binary. These can make you big black holes, but as you exchange mass in the binary widens. So you can create very massive black holes, but the binary becomes too wide to merge within the age of the universe. So it's not a good explanation for the LIGO black holes. And finally, one could, instead of using accretion of gas, grow the black hole masses through mergers. And this is something that is definitely possible. We could have multiple generation mergers in the universe. However, each time you merge two black holes, you get a recoil with velocities of order of 100 kilometers per second. So to have multiple generations of mergers, you have to have an environment that is able to retain the product of the first generation merger. And that typically means either nuclear clusters or AGN disks. And then the problem becomes, is the rate high enough to explain the observations? And finally, just out of completeness, I also want to mention that it could be that these very massive black holes in the gap are actually the result of a misinterpretation of the data. For example, we don't have waveforms to measure the black hole masses for very eccentric mergers, which could happen in a dynamical environment. There could be lensing effect, although the rate disfavor this explanation. Or if you change the priors in the LIGO analysis, people have shown that you can find solutions that are compatible with the data, where you have one black hole above the gap and one just below the gap. So what's the solution among this landscape is still completely debated. So I want to focus, of course, I'm not an expert on all of these things, but I want to focus in particular on one of these proposed ideas, which is the stellar merger scenario. And this only requires stellar physics and a bit of n-body dynamics to bridge the gap. So this stellar merger scenario was originally proposed based on n-body simulations, and it also trickled down into the LIGO publications as well, despite the fact that I would consider it fairly speculative. The basic idea is to avoid the pair instability by making a weird star that has a small core and a very big envelope through a merger. So you start with two stars that are just below the regime for pulsational pair instability. And as soon as once the most massive star finishes its main sequence, so it has a helium core, you merge it with a companion. But you assume that this merger doesn't change the core. So you still have the core of a star that was too low mass for the pair instability. But you've added the entire mass of the secondary to the envelope. So you now have a very big star with a very small core, and you assume that this star can hold on to its mass for its entire evolution. And then when it collapses onto a black hole, swallowing the entire hydrogen envelope. And remember, I mentioned at the beginning that the fate of the hydrogen envelope is really the only thing where there is debate in the literature, not really the physics of pulsational pair instability. And then you made one big black hole. So if you want a gravitational wave event, you have to put this system in a dynamical environment, such as a cluster. And then since this is a very big black hole, it's going to quickly find some other black hole that it can merge with. So this basic cartoon picture of the scenario allows me to highlight a few speculative steps that would require a little bit more studies to really be trusted. In particular, here, the treatment of the merger is very simple. You have no mass loss during the merger, and maybe more importantly, you assume that the merger doesn't touch the core, which is a very big assumption that should be checked more thoroughly. Then you have a star that is about 100 solar masses in this cartoon with a weird core envelope structure. And when we see stars of this mass, exactly like Eta Carinae, we know that they like to do mass ejections. So this is neglected here. There is the fate of the envelope, which is a point of debate right now. And finally, the need for dynamics. This is actually what the proponent of the scenario have worked out with their n-body simulations. And in particular, I want to walk you through these uncertain assumptions in a little bit more detail and try to make a simplified toy model of the post-merger structure to test some, but not all of these assumptions. So the first problem is really at the moment of the merger. And as I said, the problem is the total mass and the fact that you don't touch the core. Or in a sense, you could phrase these as a mass and angular momentum budget. So let's start with the mass problem. When you have a cluster environment and you smash two stars together, SPH simulations show us that you should expect some mass loss. In particular, this is a numerical fit to SPH simulations of low mass stars in globular clusters. And it's showing you the fraction of the total mass that is lost as a function of the impact parameter between the stars. The more head-on the collision is, the more mass you lose. And in these simulations, no radiative effects are considered. However, here we're talking about very massive stars that are at the brink of being radiation pressure dominated. So these lines should be considered a lower limit on the amount of mass loss that one should expect. And if reality is close to the lower limit, well, this is not too worrying for the LIGO measurements because they're not at the 2% level precision. A way that we can have to estimate the mass loss is just look at the binding energy of our stars. So this is the binding energy profile as a function of mass from the core, the most bound part, to the surface, the least bound part, and compare these with the kinetic energy of the merger. And if you estimate the kinetic energy using the dispersion velocity of the cluster, maybe you can justify that the mass loss would be very small. But this is not really the right thing to do, because when the stars will be merging, they will reach each other with a relative velocity that is of the order of the escape velocity from the surface, which is going to be much higher than 10 kilometers per second. But still, here to make my toy model, I'm going to follow the assumptions of the proposed scenario and assume that in the merger, no mass is lost. But I really want to emphasize that this should be tested further. The second issue is the angular momentum budget. As soon as you're not a perfectly head-on collision, you will have some angular momentum that you have to put somewhere in your star. And if you put it at the surface, then you can get centrifugally enhanced mass loss, which decrease the total mass that you have available for your black hole. So that's maybe not very good. The other place is putting it in the core, but then you're going to get rotational mixing that is going to make the core grow. And by construction of the scenario, we were just below the pair instability regime. So if your core grows, you hit the pair instability and the scenario doesn't work anymore. But again, since I don't have the tools to run hydrodynamic simulations of a merger at hand, I will follow the assumptions of this scenario and make non-rotating models. So if we follow these assumptions for the merger process, we can then build by end a merger model, which will clearly be oversimplified because of the way we're treating the merger. And to build this merger model, well, the ingredients that I have are the two stellar structures at the time of the merger. So here I'm showing you the mass fraction of hydrogen and helium as a function of mass coordinate. So again, 0 is the core and the maximum is the surface. And these two profiles of the two stars that I'm going to merge are taken at the end of the main sequence of the most massive star. So the core of star 1 is pure helium. And then you have your envelope stratification and composition. But an important point that is neglected in the original scenario is that very massive stars have very similar lifetimes. Basically, they all live 3 million years. And so at the end of the main sequence of star 1, star 2 is already 75% helium in its core. And when you do the merger, you have to put this helium somewhere. And now intuition would suggest that you get some sort of entropy stratification, that the densest part sink more, and so you put the two cores together. If you do that, you're not avoiding the pair instability. So we cannot do that by construction of the scenario. What we can do is have two different models that bracket the range of possibility. The first one, I'm going to take all of star 2 and mix it completely throughout the envelope of star 1. So this is what these solid lines in the bottom panel give you. I take the core from star 1, and then I create an envelope by mixing everything else of star 1 with the entirety of star 2. This gives you a helium-rich envelope because you had the helium of this core that ended up in the envelope of the merger. And although it assumes that this core material can mix with this surface material here, which is questionable. The other bracketing case is, well, let's forget about the evolution of star 2. This could make sense if you have a cluster where you have a star formation history that has some spread in time, and you can form star 2 after 3 million years after the formation of star 1. And then as soon as star 2 appears, it merges with star 1. And that would give you the dashed envelope, which is less helium enriched because we're not introducing any new helium in our model. And if now that I have these two initial profiles for a merger structure, which again are very, very simplified because of the assumptions that we're making for the merger, I can let them evolve and see what a star like this would look like. And so the next plot is showing you an HR diagram for these two stars. So you have the luminosity on a log scale, the effective temperature in a flipped direction, and the tracks in blue and red evolve from left to right, like in a normal HR diagram. The blue track is for the model where we mix the secondary star in the envelope. So it's helium rich, and that's why it's more luminous. The red track instead is our model where we neglect the evolution of the secondary. And here each dot is at 500 years of time. And so you can see that these stars spend a significant amount of time in this gray box. This is the S Dorados instability strip, which is an observational part of the HR diagram where we see stars undergoing luminous but variable eruptions, these big eruptions where stars have huge mass loss rates. And then afterwards, these stars evolve beyond the Humphrey-Davidson limit, this dotted line, which is again a region of the HR diagram where we don't observe stars. And people think this is either because they spend very little time there or because when they enter this region of the diagram, they become unstable. And this is what is happening in these stars. You can see these huge spikes. These are related to our stars becoming super Eddington in this range of the HR diagram. And so this HR diagram, the position of this model and the behavior of the model really suggests that we should expect some ejection of mass from these structures. Unfortunately, we don't have a good theory for what drives these mass ejections, so I cannot model them. But there are theoretical ideas in particular that suggest that helium-rich stars might be more prone to these instabilities. And in the blue models, we have a helium-rich star because we have helium in the second star that we have to put somewhere. And again, I want to bring in Eta Carinae here because the best models that we have for the giant eruptions of Eta Carinae are precisely these, a merger between two very massive stars that produced huge outbursts of mass loss. So here I'm trying to put together Eta Carinae and this merger scenario for black holes in the gap in a provocative way to kind of question this idea. Nevertheless, I can also let's follow the scenario for one more step and assume that these mass loss processes that should be expected are not happening or they don't remove much mass. Then the next question is, what is the fate of the envelope at the onset of core collapse? And there are many ways in which a star that forms a black hole at its death can lose mass. The first one is through neutrino-driven explosion, even in the case where you form a black hole. The second one is these stars could be rotating and form a collapsar. That is, the infalling material forms a disk around the seed black hole, and then this disk blows up the outer layers of the envelope. And this has been shown it could happen also for non-rotating stars that have thick convective envelopes. And finally, there's also just the sheer fallback and the release of gravitational gravitational potential energy under the form of neutrinos can drive a fallback powered explosions. And these are all very active topics of research today. So although I only have toy models of this merger structure, I can try to do some tests about the fate of the envelope. And the first test that we can do is take our model at the onset of core collapse and run it through a 1D supernova code. This 1D supernova code allows us to calculate the flux of neutrinos. And what happens is that the black hole that you form has a mass that is smaller than the mass of the core that is collapsing because you're losing mass to the neutrinos. And this neutrino loss happens on a time scale that is shorter than the free fall time scale of some outer layers. And so for those outer layers, this is an instantaneous change. And these outer layers react by triggering a pulse wave, a wave that steepens into a shock in the outer layers and removes some mass. So here you're seeing the mass as a function of time after core collapse for the black holes that we expect. And from the scale of the plot, you can see that this is a small mass loss mechanism for our models. And the reason is that our models are still fairly blue when they collapse. And so they don't have a loosely bound large envelope. However, this is again something that I'm testing on a toy model of the merger, and more sophisticated merger models would be needed to really hammer this down. The second thing that I can check is, can I form a collapsor? Can I have a disk that blows up some of my envelope? My models, I remind you, are non-rotating. So the only angular momentum that I have available in the star is due to the motion of convective blobs, which randomly can bring in angular momentum. And here the red curve shows you this random angular momentum as a function of the time it would take for a convective layer to fall onto the center of the star. And instead, in this orange-blue, you see the innermost stable circular orbit angular momentum for an initially non-rotating black hole that accretes the mass. And from the fact that the red is always lower than this blue-orange curve, we know that in this non-rotating model, convective layers never have enough angular momentum to trigger the formation of a disk. But again, this was a merger. And where did we put the relative angular momentum of the two stars is still an open question. So here I'm just showing you a toy model to highlight a potential issue with this merger scenario. And then finally, the actual part that has been worked on extensively is, even if everything goes well up to now, we made one black hole. And we need some dynamical process to form a binary black hole that merge within the age of the universe. These people that do n-body simulation find that is possible. And actually the key here is that very massive black holes sink very quickly to the core, and they can find very easily companions to merge within. And in particular, you can see that in this cartoon, the whole delay time between the forming of the stars and the merger of the black holes is of order of tens of mega years. So this is a rather rapid process. And if it happens in nature, we should be able to find the clusters where the black holes formed, because in 10 mega years, there will still be lots of stars around that were lower mass and didn't form black holes. And if you want this to work for the most massive gravitational wave event detected so far, you actually need this weird merger process to happen twice, because both black holes are solidly in the pair instability mass gap. And because of the variety of other possible solutions and the many uncertain steps in this scenario, I would personally not consider this scenario the most promising explanation for this tail of black holes in the LIGO distribution. And so I think I'm probably running out of time if I'm not over it already. So I hope that in this talk, I convince you that from the shape of the black hole mass distribution that we're finding through gravitational waves, we're getting the first solid, non-controversial evidence for pulsational pair instability in nature, and that the tail of black holes that should be forbidden according to this process, it's not clear what the explanation is yet, but most likely it will require dynamical interactions. And if you want the dynamical interactions to act on the stars rather than directly on the black holes, then you will require the stars to merge in a weird way and to swallow their entire hydrogen envelope when the black hole forms, which is still debated in the literature. And that's pretty much what I wanted to tell you. Thank you.
Thank you very much, Matthew. Then, Gloria, please, we can perhaps move to the questions. Please, Gloria.
Okay, thank you, Matthew. Very, very interesting talk and very clear. There's only, I guess, one thing that I'm confused about, and it's the following. if you were to start out with a binary system in which both stars have, say, 85 solar masses,
Mm-hmm.
and you had an extremely high mixing efficiency,
Mm-hmm.
forget about how that's done.
Sure.
You just have a very high mixing efficiency so that both stars evolve according to chemically homogeneous tracks.
Yes.
Are you saying that they will hit the pair instability, or
Yes.
they're not? They won't.
They would. My expectation is that they would. There is work from Pablo Marchant and Takashi Moriya where they taken helium cores, which is exactly your scenario. Mixing is very efficient. We don't know what does it, but it's just a helium core. Added rotation and computed the pulses anyway, and they find that the gap doesn't move that much. They found a 4%, if I remember correctly, actually I might have even a backup slide showing that. Here, okay, so these is the temperature density diagram. These contours here show you the instability region, and the instability region shrinks a bit if you make the model rotate very fast, but they only find a change of about 20%, assuming the most optimistic fast rotation of the core. And only if you use a more realistic coupling, by which I mean the Spruit-Taylor dynamo, you'll find a variation of only 4% of the location of the gap in black hole mass. And if you believe Jim Fuller's model for angular momentum coupling, the cores should be spinning even less at the end of the evolution when the pair instability kicks in. So I think chemically homogeneous evolution is not a way to avoid the pair instability gap.
Okay, just one clarification. When you say rotating as fast as is allowed, the as is allowed, what's that condition?
Sorry, poor phrasing from me. What I meant is that they assume no coupling, like to find this 20%, if I remember correctly, they assume no coupling between core and envelope. So you start with rigid rotation, and then your core contracts and spins up without giving back any angular momentum to the envelope, which is not what we think happens in stars based on astroseismology of low mass, 3 solar mass stars. Does that make sense?
Yeah, so what you're saying is that the very rapid rotation, if it continued to rotate as a rigid body, it would hit the critical rotation velocity and would lose mass. Is that what you're saying?
Oh, no, I was not even going there. That if you turn on like the enhanced mass loss through winds, then maybe your core will become so small that you avoid the pair instability. That is possible. What I was saying is that if you assume that your core is just an isolated ball that doesn't communicate with the envelope, so it keeps its angular momentum, as the evolution proceeds and the core contracts, its spin is going to go up.
Yes.
But even in this optimistic scenario, the rotation is not enough to prevent the pair instability. And so you would still pulsate if you're massive enough, no matter how fast you rotate.
Okay, I think I want to look at those papers. Thank you.
Yeah, sorry.
No, that's okay. It's a very interesting question. Thank you.
I saw first Alan's hand, but there is not now. Then we can move to Enrique, please.
Hi, thank you for the nice talk, Matthew. So if you were to bet on what's the formation scenario for something like
1905-21. Yeah.
So you even put a chart there with different kind of formation scenarios. So what would you bet on?
So of
So
course,
it's
this
kind
is
of like an opinion. Sorry.
yeah, exactly. This is just my opinion, might be wrong, but right now my best bet would be AGN disks, partly because of the tentative association of an electromagnetic counterpart to this event. Also because AGN disks would provide you an environment, or AGN disk or a nuclear star cluster would allow you for multiple generations of mergers, which help growing the mass. And recently, people here at CCA, Matteo Cantiello and Adam Germin, have proposed that maybe stellar evolution in the disk could push towards more massive stars. So within the context of AGN disks, there are at least 3-4 different ways that you can make a black hole in the gap. And I think that's most likely, like that has the highest chance of being the right explanation, I would argue.
Okay, so this is regardless that the signal seems to have a different Z or different distance and a different, so more than a month.
So yeah, this is a very good point. I was puzzled by that a lot, but actually it seems it's a confusing presentation of the results. Talking to gravitational wave people from LIGO, the redshift is actually not incompatible. And I'm not enough close to the data analysis in LIGO to really explain this, but they are not incompatible within error bars, the redshift of the electromagnetic counterpart and of the gravitational wave event.
Right, but still you have a month between.
Oh, this is
expected. The two signals, right?
The delay time is expected because you merge your black holes, maybe in a gap of the AGN, like due to, say, migration traps. And then the merger gets a recoil and you need time for the merger, the recoiling merger to hit some gas. And that is about a delay time of a month or so, at least they claim.
All right, thank you.
Sure.
I don't see more questions. I don't know. Somebody else?
Yeah, sorry. I was just curious about the figure showing the results from LIGO, this distribution in mass.
Yes, I'll try to find the nearest one. This one?
Yeah, I was just curious. What is the meaning of the different lines?
Oh, the different, so there is one particular event in LIGO, GW 190814, I think, where it's a merger of a 23 solar mass black hole with a 2.7 solar masses compact object, which we don't know if it's a black hole or a neutron star. And for this reason, that particular event can be removed by the analysis. And so I think the dashed line includes it, and the solid, the solid line, this one, does not include that particular event. That's the difference between the two.
I see. And then the shaded area is just like
98% interval, confidence interval.
Okay, great. Thank you so much. And thank you for the talk. It was very interesting.
Gloria?
Yeah, so let me get back to my chemically homogeneous binary. My internet connection is unstable. I hope you'll hear me and I don't freeze.
Yeah. No, you're fine for now.
Okay. So if you look at it backwards and you say we don't have a large number of observations that suggest that we observed pair instability supernovae.
Yes, arguably yes.
Would that then impose a constraint on the characteristics of the chemically homogeneous binaries, which one might hope to have eventually? Or I would like to constrain the mixing in terms of mixing.
So first of all, yeah, from electromagnetic observations, we had, well, it's debated whether we've seen one or not, but that's not very constraining because the masses required for this process are so big that this phenomenon is so rare in the universe that it's conceivable we had not detected it yet. Of course, LSST and these large time domain surveys will change this. If this exists, we should find it at some point in a way that everybody agrees. In terms of using detections of pulsational pair instability supernovae to constrain chemically homogeneous evolution, I would be worried because chemically homogeneous, like this is two special things that don't necessarily go together. They could, of course, because through chemically homogeneous evolution, you can make bigger cores and reach the pair instability regime. That's maybe what you have in mind, but that's maybe not the only way to do that. And so I'm not sure how do you break the degeneracy, for example, from with the slope of the IMF at the high mass end, say. Because there are other ways to get big cores that don't require chemically homogeneous evolution.
Okay. Okay, I see what you're saying. Good, thank you.
You're welcome.
I don't see more questions. Then I just want to thank you again for the talk. It was very good. And well, we can turn on our camera just to say thank you and goodbye.
Thank you.
And for the rest of us, see you next week. Thank you very much.
Okay.
Bye bye.
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 Thank you for inviting me.
Thank you.
Bye. Yes.
Thank you, Matthew.